Yes, my name is Liu Jian. I come from China. Is the South China AE manager. So today I will bring some topic about the powertrain of the automotive test solution from Tektronix. So let me share first. So can you see my screen?
Yes.
Yeah, I think my colleague Bernard has some difficulty accessing the room now, but maybe we can start. Okay, so it's today's agenda. First, we first give a brief introduction about the EV power analysis, and also some scenario about the EV supply equipment testing, and also the converters power analysis, and today's latest wide band gap testing, major focusing on the double pulse testing, and also how we see the high voltage probing in the real testing scenarios. And also we'll bring some topic about the IMDA inverter motor drive analysis toolkit, and also some in-vehicle network analysis, which is focusing on software-defined vehicle right now. So let's move on. So I can make sure that you can all see my screen.
Yep.
Okay. So right now, if we look at the whole EV ecosystem, you can see that there are uh, several major parts, like the powertrain, mainly focus on today's topic is motor driver, motor battery testing, and even the power converter inside the powertrain system, which is the heart of the EV. And also to provide enough power and all what we so-called the new green energy of the EV. We need in infrastructure like the grid, like renewable power charger, which are also important. And when you're talking about the latest automotive, we're also focusing maybe ADAS and information infotainment systems inside the vehicle, which is more focusing on user experience, and also we cover some in-vehicle networking, something like this, and also we have some traditional part, which is has some new meanings inside, like the body part like lightning, keyless entry, and also we have the chassis like TPMS. That's the whole ecosystem of the EV, and it's quite a big topic. We will focus on the powertrain today mainly, and if we have other interesting part, maybe we can uh, spend more time maybe later to introduce more about it. How can I? Okay. Okay, and when it comes to the EV powertrain, here is the uh, diagram. You can see that from the power, it comes from the DC power charge, and it will charge the battery pack of the EV, and then this battery pack will also provide a DC-AC converter or controller to control the motor to drive the EV to move, right? And also we have a AC charging, which we have a OBC onboard charger, okay, which can slow charge the battery pack. So in this kind of simple block diagram, you can see that we have this kind of charging pile, and we have the inverter and motor drive inside the vehicle, and also we have the OBC and DC-DC converters, which is the major power chain of this whole EV. And inside this EV powertrain, we have a lot of measurements. Here we can see we have some more detailed diagram of this EV powertrain. We have the control unit to control the traction inverter to drive the motor, and also we have the DC input. So inside this different blocks of the powertrain, we have to do a lot of measurements. For example, like the power quality, both the input and output of the DC-DC converter or AC-DC converter. We also need to measure the harmonics, and also we care about the DC ripple, which is quite important for the DC bus quality. And also we always care about the efficiency of the inverter, to enlarge the traveling miles of the EV. And also we need to study the control algorithm for the controller. We use the DQ0 analysis tools, which normally is inside the SoC or the MCU of the control unit, but we need to find a way to study how this control is workable or not. And also we have a lot of mechanical measurements need to care about, like the motor speed, direction, angle, torque, mechanical power, exaggerate. This kind of mechanical measurements we need to combine with all these electrical measurements to see how our control is efficient or not. And if we dive a little bit deeper in the power converters in an EV, we can see that it's almost everywhere. First, from the EV battery module, it has to convert from DC to DC by its high voltage to the low voltage DC. We need a DC to DC converter. Right now, maybe in the market, a major EV is 400 volts high voltage, but the whole industry is transforming to the 800 volts high voltage to 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 achieve faster charging speed, to heal the anxiety of the traveling miles. And also from the low voltage DC, we have the low voltage battery, which is DC to DC converter to all those components inside the vehicle, like the infotainment system, like the Viper, like the air conditioner, exaggerate. Here is the DC to DC converters in different category and different levels. And also when you're talking to the motor drive, we need to have a DC to AC converter so that we can control our motor in different kind of scenarios. So all the things is quite similar, like the traditional power supply or the power converter. So on the power chain measurement, we need to borrow a lot of testing methods and testing setup from the traditional, power industry, but it has some more new meanings. But anyway, if we look at the power converter diagram like this, we have different stages. Like we have the input filter, we have the switching components or the switching circuits, and then we have a transformer and the rectifier to get the DC out of the power converter. And also we have the control feedback loop to using the PWM methods to control our switch, the stages. So if we look at this whole diagram, you can see that from every stage we have a lot of testing to be measured. For example, for input, if it's AC or anyway, it might be DC input. That's fine. But anyway, if for the AC power input, for example, if we have an onboard charger, it's AC input, and we have to convert to DC for charging, and we have to measure the current, voltage harmonics, the power quality, in rush current, and also the input capacitance. When you're talking about the active components inside the switch stage, we have to take care of the switching loss, the SOA, the slew rate like DIDT or DVDT, and also the RDS on to make sure we have the minimized switching loss and maximum efficiency. About our switching. And then when we're talking about the output stage, we have to measure the output DC voltage like a ripple, efficiency, and also the turn on and turn off time. And also we have to take care about the magnetic loss inside the transformer, which is something like a component. And we have to care a lot about the magnetic loss. We need to care about the magnetic properties, inductance, and also I don't know how to say it in English, but that's fine. But this is also what we care about because we need high efficiencies. And when talking about the control loop, we also have the frequency response analysis. We use the Pro methods to calculate the control loop response since right now we are in the EV we have a huge load changing, so we need to make sure the control loop have enough margin for the stable loop of this power supply. And also, if we are thinking about how the DC to DC convert, or even to the the final stage of the power delivery, we need to care about the PSRR, power supply rejection ratio. And also, we need to care about the PDN network impedance, since we have a lot of high current, fast switching loading, so the impedance is need to be low enough so that we can achieve the stable power supply on DC. So all these measurements apply to whenever it's DC converters or AC to DC or even DC to AC converters. Okay, so we can separate them into different stages. So we start from the switching devices. It's the switch loss is very important, and also when you're talking about this kind of EV, we need to characterizing our switching component like the IGBT, like the wide band gap semiconductors. So we need to measure the switching, the parameters, and also we need to find out the limit of our components. So here we need to measure like the switching parameters like turn on and turn off energies. And also we have to care about the switching time analysis. And also we need to measure the output capacitance of the switching components. And when we're talking about the diode reverse recovery, we need to measure a bunch of tests like the recovery charge, recovery energy, time and current, and also slew rate. And to doing this kind of switching testing, normally we are using double pulse test methods, which we might be mentioned later in a bit more detail. But anyway, this double pulse measurement using 3 different steps on this half example, half bridge circuits, so that we can see how these switching components working in different stage, like open, like the closed stages to see how these parameters can be measured. And also in the EVSE, we have the AC and DC charging. Normally, we have the grid-tied AC, which comes to a DC fast charging station. Inside that, there will be AC to DC modules and also DC to DC converters to adapt to different requirement of the EV DC voltage requirement. So normally we categorize them into 3 different levels. And for fast charging, it's level 3, and it converts the AC to DC, which can provide a much faster charging times. And also, when we are using H charging, you use the onboard charger to convert to DC to the battery. And normally it's using connected to this might be less than 240 AC voltages to the EV, and you need a long time to charge a car. And inside the EVSE, it's quite similar like the power converter we mentioned before. It has the, for example, the DC charging pie. It has the 3-phase AC inside, and then it converts to the DC, and then it has the power factor correction modules and output stage DC to DC converter to the vehicle interface. And inside this vehicle interface, we have different kind of standards like Euro stand, American stand, and also like the Asian stands. It has the DC power supply, and also it has some communication like CAN or PLC to the system controller inside this charging power. So, and also it has some external communications, maybe some Ethernet connections, maybe some HMI, like the display or something like this. It's the major function blocks inside this charging power. So, but when it comes to the real measurement, or when it comes to hardware design, it also has the quite similar, the architecture of the power, converters. But anyway, in the EVSE, we hope we can achieve higher power factors. And also, we need to achieve sorry.
Apa yang mau dibahas, Pak? Sabar.
Okay, so we have to achieve as low as harmonic distortions to fulfill the regulation. And also, we need to have higher efficiencies. And the measurement is quite similar as the power converters. So when it comes to the interface measurement, we have to make sure the communication is good. So we need to measure the signal qualities of the communication. And also we need to measure the duty cycle of the control pilot, system timing, even the noise. And sometimes we are doing some debugging, we might doing the CAN bus decoding. And also we need to make sure the output can fulfill the regulation. That's the measurement of the EVSE interface. So as you can see, the inside the vehicle or even the EVSE, we have to measure a lot of converters. So we can go into some detail of the power analysis. This we have mentioned before. And in fact, right now in our scopes, we provide the whole software which we can do all this testing, like the input-output, voltage quality, power qualities, switching, control loop, magnetic analysis in just one single scopes. So here is an example of the power quality. You can see that we can measure the voltage and current of the system, and then the software can calculate all these power qualities, and it can list the results in this kind of table, and we can output it to our PC also. You can see that we can measure, for example, like the crest factor of the voltage and current, like the true power, reactive power, something like this. And also inside the scope power analysis, it has the harmonics measurement also. And we always hope that the load is resistive and the current and voltage are in phase, and no harmonics at all, but it's not always ideal. But anyway, inside this power analysis software, we can measure the harmonics under different standards, and also we can customize our, the limits of our harmonics. So here we can see that the three-phase voltage and current harmonics can be shown. Here it's using IEC 61032 class A example. And also inside the scope or in the power measurement, we also care about the inrush current and the input capacitance. This can be done by just select the measurement by just one click. Here you can see the inrush current, the maximum and the minimum results. And we have the mark here to see how the measurement is inducted the area. And also we can calculate the input capacitance by simply measure the voltage and the current to get capacitance. Oops. And also switching loss, when you talk into a switching loss measurement, the software can just edit the switch loss measurement. It can do like the turn on loss, turn off loss, and also the conduction loss automatically. Now, because inside to measure this kind of switching loss, right, we need to find the specific voltage or current threshold, and we need to do a lot of mathematics to calculate those switching on and switch off areas, and to find out the loss, do some like integration or something. In the software, it can help us to define what kind of turn on and turn off scenario is, and it will give the results very directly and easily. So you can see here this example. It can help us to identify the loss regions by annotation. And inside the software, it can also add a SOA, safe operation area measurement. So here we can see a very typical result, how this SOA mask is added. And we can manually input these SOA areas by ourselves. And the slew rate of the voltage and current is also important for the switching analysis, like DIDT, DVDT. It's very important because it helps us to, which can optimize our slew rates to get as low as, for example, the switching loss, increase our efficiency, but we also need to maybe doing some trade-off, for example, about our harmonics and about some EMI problems, and DIDT and DVDT is very important. And on this switching loss analysis, it can easily help us to measure all those things. One thing maybe we need to care about is that in our measurements, like DVDT or DIDT, you can see that we are not just measuring one instance of the switching area. In fact, we are measuring the whole records of the scope. So if we can see here, for just one single acquisition, we can measure all those instances. Like here, you can see the N, it says the 329. It's not only done by multiple acquisition. It can be done by just one single acquisition. It can measure all those switching areas to provide the results, which is very helpful because we can measure continuously, the switching periods, and we can find out even some clues or even some trends inside this kind of slew rate measurements, because sometimes it's not maybe stable. If you change a little bit, it might have some other unknown issues inside. But in traditional or in conventional measurements, if you are measuring DVDT or DIDT, you can just measure one instance in one acquisition. If you need to continuously, acquisition the waveform to get a large amount of results, and also we can get those stable results. But all these in this kind of conventional measurements, all these results, they are not timed continuously. They are one acquisition after another acquisition. There are a lot of gap in time. So in our slew rate or switching analysis softwares, it can measure continuously and provide even the time trend analysis of the result. And also, we can provide the RDS on, which can help us, very easily to measure those RDS on directly. And when talking about this switching, we also need to care about the magnetic loss. So in fact, in our software, we can measure simply by measure voltage and current, and can provide a BH curve. And by using this kind of BH curve, we can easily to find out our inductors parameters and what we need and what's the magnetic loss. Here is an example. If we can see, they can provide a lot of plots, and also we can doing continuous measurements. We can provide like the inductance measurements to magnetic loss through the BH curve, and also can provide a lot of magnetic properties that we might be interested in. And also, when it comes to the output of the DC to this converter, or output of the DC, we always care about the ripple of the DC voltage. Is also very important. And we have the ripple items, test items, just by singly by click the measurement items. And when it comes to the power efficiency, we might have the input as AC or input as DC. And also we might have multiple power rails to provide the output of the DC. And the good thing is that our scope, the software can provide maybe up to 3 outputs, which can be related to the multi-channel of our scopes. For example, here we have 4-channel scopes. We can measure the power efficiency by 1 input, 1 output, and it can reach up to 1 input and 3 outputs at the same time by using 8-channel scopes. And we can specify the voltage and current of our scope channels. Then we can easily get all these results. Here is a simple example of how this power efficiency is conducted. And its good thing is that we have the multiple channel, so we can doing this 1 input and multiple output at the same time. And if we have, maybe I will cover later, we have the tech scope, the software on the PC, which can connect more scope channels to doing even more channel measurements by synchronizing multiple scopes. And inside the power analysis, we have also the the turn on time and turn off time measurements, and we can identify our turn on and turn off scenario, and it can automatically find out the timing and sequencing of the power supply output. Normally, if we don't have this kind of testing, maybe we need to using cursor 1 by 1 to measure, but turn on, turn off time items is easily just click and measure all these requirements. Faster and easier. And also, right now we are using faster switching components. We have also a huge loading change for our the power supply output. So we need to have a stable control loop. Right now, more and more, the power supply or the EV manufacturing care about this kind of frequency response analysis, like board plot. And normally, in traditional way, we might have those kind of control loop analyzer, but for the engineer, it's sometimes it's difficult because he has to learn not just scope, he has to learn another new instrument. But right now we integrate all these board pro measurements inside just one scope. So for engineer, we just need to use one instrument that we can do all these measurements. Here is a simple connection diagram, which we can also find in our application node or in our software. We can using our 5 or 6 serial scope with our power analysis software. You can have this kind of test items, and we can using just 2 channel of probes and the AFG inside the scope. Then we can do all these control loop measurements. We have inject transformer, which can put the stimulus signal from the AFG of the scope and inject it to our control circuits. By using 2 probes, we can measure the input and output of the control loop and get the results. Here is a real example. You can see here, you can easily measure the gain margin and also the phase margin of the control loop. We have done a lot of testing and a lot of results correlation with the VNA or the control loop testers like board E100. So the result is very, very similar since the scope has up to 12-bit ADC, and it can reach a higher dynamic range than before. Here is an example with larger screen captures. And also, if we care about the DC to DC, maybe or even the LDO on the final stage of our circuit, the power analysis software can provide the PSRR for our DC to DC converters. Quite the same, but it's using a different injector. We have an external power supply to provide the input power, and then we have the interference from the AFG, and we can measure how this power supply rejection ratio is. Here is an result. You can see that even in PSRR, in traditional way, like if we have, for example, 8-bit scope before, then people will say that, okay, PSRR is not good enough because normally in some LDO, it might have more than 80 dB or even 100 dB dynamics for the power supply rejection ratio measurements. But here is a real example. You can measure 104 dB for the rejection ratio, which is really impressive. And when it comes to the power distribution network of the circuit board we have for the scope can also provide the impedance measurements with different transformers, but also using AFG inside the scope, we can provide a signal stimulation. Also, we can measure accurately the impedance to see how our power distribution network is good or not. Here is also an example. Normally, we hope our impedance of the PDN network should be as low as what we need, so that when the current change significantly, our voltage distribution is still stable. Here is an example. So we just go through a little bit about how those power converters related measurement in just one scope software PWR, and then it can provide like the input and output power quality, right? Our switching loss, magnetic loss, and also we can measure the control loop, and also those kind of PSRR measurements, which is quite sophisticated and cover almost all the requirement measurement inside a power converter. But right now we have new things coming is the wide band gap semiconductor inside the EV. Since we need a higher voltage, we need to have a higher efficiency and less or higher power density. Then it comes to the wide band gap semiconductor. And the major measurement of the wide band gap semiconductor is the double pulse testing. So right now we provide this kind of testing items or the testing software. We call it double test DPT options. In fact, we can use the double pulse on 1, 2, 3 different voltages to see for the first pulse. Normally it's setting up the IGBT or the MOSFET or the wideband gap semiconductor to the conditions or to the currents it want. And also we can measure the turn-off parameters by this kind of areas. And then we can use a second turn-off the areas to measure something like the reverse coverage parameters. And also we have the third one to measure the turn on time or the turn on parameters. This is called the double pulse testing. The important thing is that we need to have this kind of flexibility so that we can adjust the pulse width by what we want or by the conditions we want. So in the software, we have the control of our AFG inside the scope to help us to easily change the pulse width and to get the testing conditions we want. The difficult thing right now, or the challenging right now, is the wideband gap. Right now is getting to the vehicle already. Both are the OBC, main drive, also the charging pile are using this kind of 800 volts technologies. Here is a simple diagram of the trend, how this will be using the new semiconductor technologies inside the vehicle. It's already started. Right? So we need to measure higher voltage, the how to say, silicon carbide MOS and faster switching loss. This comes to a lot of tester challenge. It's quite different as before. The big challenge is that, for example, in a half bridge circuit, normally we need to measure this kind of VGS. I didn't bring the data sheet here. If we look at the silicon carbide, normally it's about less than 20 volts for this kind of VGS. But the bad thing is that the common voltage is really high. Here is an example. It's using a 600 volts common voltage on the upper arm of this half bridge. We need to measure 5 volts VGS. Then if we want to measure this kind of 5 voltage, we need to have a really high common voltage rejection so that we can easily get the results. We can do some simple calculation. For example, if the common voltage rejection ratio is, for example, 40 dB, which means 100, times attenuation of the 600 volts, which means that the output or the common mode voltage will be 6 volts already, but we need to measure a differential voltage at 5 volts. This kind of a common mode rejection is not good enough. We need to have even higher, for example, like 80 dB, which means that 600 volts common voltage at the output will be attenuated as to 6 millivolts, so that we can measure the 5 voltages accurately. So here is an example by using the neon probing technologies. If you are using a 40 dB common voltage rejection ratio, you can see here the 6 volts errors here. It's really huge. It's difficult for us to measure the 5 volts. But with this kind of higher common voltage rejection ratio, you can see the common voltage is really small, and then we can measure accurately. So when it comes to this kind of a measurement, we need to know that in normal high voltage differential probes, we have the typical CMRR spec in the datasheet. Here is a quite classic high voltage differential probe, THDP 0200 for Tektronix. You can see that for the typical CMRR for DC is 80 dB. Looks really good, right? But when the frequency is rising, you can see, for example, 100 megahertz above, the CMRR is already decreased to 26 dB, which is really small. So the bad thing is that when it comes to wideband gap or silicon carbide semiconductors, the switching rate is really, really fast than before, maybe 10 times or even more, which means that the frequency is higher than before. At this kind of scenario, the traditional differential high voltage probes is not good enough since the CMRR is decreased. So here is a plot of a typical differential probe. All mentioned that it has high CMRR as the selling point, but if we look at those frequency plot, we can see that it's already very poor when the frequency is raised to 100 megahertz. So how we gonna face this kind of test measurement challenges? Tektronix developed ISOView technology, which is optical isolated probe systems. It can do first really high common voltage rejection, and also it can achieve, higher bandwidth like 1 gigahertz, which can, face on the nanosecond rise time measurements. And you can have 120 dB CMRR for the high frequency requirement. So here is the comparing result. We can see that for this isolation probes, even when it comes to the 1 gigahertz bandwidth, it can still have above 80 dB CMRR, which means that it can attenuate it, the common voltage on 10,000 times. So even we measure the 800 volts, common voltage, the output of the common voltage will be only like 8 millivolts. So it's really good for us to measure this kind of wideband gap, semiconductors. And another thing is that it can provide 5 differential front end from 5 volts up to 2500 volts. So we can measure like a VGS, VDS, or in different scenarios, but have the same, common voltage, the withstand pressure like 60 kilovolts. But to achieve this kind of specification and measurements, we'll design a differential front end. And also, we suggest our customers to design some test point with lower, heuristic parameters, so that the measurement can be accurate enough. So it's cooperation between testing companies and also the hardware engineer. We need to cooperate to design our testing and measurement circuits also. So here comes some real example we measure at customer side. Here we can see the silicon carbide MOSFET. We measure the VGS at the same point with our isolation probe, in traditional, high voltage differential probe. So we can easily to see that the CMRR is taking great effect for the isolation probe. It's really clean. Customer is wow. They never know that they can measure this kind of accurate signals because they are normally watching on these ugly results. And when it comes to real measurement like the switching laws and some other measurements, we need to find the identify the areas to calculate these results. But if we have a higher common voltage, all this kind of measurement is inaccurate already. So they have to do it manually and by using their experience. But by using this kind of isolation probes, the result is good. Here is also an example when we measure on the VGS. It's a 400 DC. You can see the differential probe is a lot of ringing here, but for our isolation probe is clean. So with this kind of excellent probe system, then we can set up our double pulse testing. Here is an example how we're gonna do this. Here is the high side of this circuit, double pulse testing. We have the power supply from Kisley, it's 2470. It can provide this kind of power supply, and then we use the AFG 312552 to drive the gate of the silicon carbide to make it on and off. And then we can have our isolated probes with different, the front end. For example, if we are measuring the VGS, which voltage is a bit small, so we can use like the 10x MSX tips to measure VGS, and then we can use our another front end of the TIVP to measure those upside VDS to see how these signals will be. And here, sometimes if our switching is not fast enough, we can use the traditional differential probe to measure the upside VDS. And we can also using our isolated probe to measure it here, because it can provide higher bandwidth. And for the current measurement, since the switching speed is faster than before, so right now we can use the current shunt method to measure the current with serial resistor inside the circuits, very small. And then to measure this kind of current, you also need to have a higher, the common voltage rejection. So we use the isolation probe here to measure the voltage as we get the current of the upside, which is more accurate than before, or than traditional current probes also. But for low side measurement, it's easily because it don't have this kind of high common voltage. So we can use some normal probes like the THTP series to measure the low side VDS. You can use our standard passive probes, but which is good. You can have a 1 GHz bandwidth, which is the highest bandwidth passive probe. You can measure the VGS, and also you can using the isolation probe with current shunt technology to measure the current here. But for the current here, we can use our TCP current probes to measure it. It depends on how fast or how the bandwidth will require to measure the current here. And also we use the FG to doing the double pulse, the simulated signals. Then we have the software. Because we have already the excellent isolated probes, we can face the challenge of the wideband gap devices. But also we have this kind of software options. We call it WBG DPT. It already integrate like the switching parameters, like the diode recovery analysis, and also the capacitance analysis already. So we can just using this software and making the measurement easily. The difficult thing is that we always are facing the noisy signals like this. So in the software, we design a lot of methods to help us. For example, finding the accurate edge by using some algorithms. So we can put the parameters here to remove the ringing to get precise edges, which can help to make the switching, transition measurement accurately. Here is an result, and all this can be done by programming also. So some customer also using, for example, integrate the software in their automation systems to do all these measurements. So to face this kind of wideband gap devices measurements, we have the excellent scope, the excellent, the isolated probes, which can reach, 1 gigahertz bandwidth to facing the fasting switching components. And also we have the power supply, the gate driver, and also the software to make all our, wideband gap measurements, confident. And you already mentioned that we have the power analysis, we have the wideband gap measurements for our latest silicon carbide technologies in vehicle. Another important thing is that how we're gonna measure our, inverter model drive, the control evolution, the control, the qualities. We have another software, we call it IMDA. And it can facing different kind of motors. I won't go through this because it's not my major. But anyway, to control all this kind of motors, we have different kind of drives. That's important. We need to make our motor working in the right situation we want. So in fact, this kind of software can be focusing not just automotive, but industrial, consumer, and also MilGov. We have all these kind of testing requirements. But anyway, we have to focusing, for example, in EV, we need to focusing on the, the powertrain designs. So when it comes to the motor drive, you can see that it's quite similar. We have the converters and the DC bus and the inverters to drive the motor, and quite the same like power converter. So I will go next. So if we see from the blocks called converters, we need to measure the three-phase power qualities and harmonics. We need to measure the DC bus and inverters we mentioned before. So we have all this kind of software like IMDA, PW power, analysis and the wideband gap, all these things. And the difficult thing is that for the motor, we have to have some mechanical analysis to measure the speed, angle, direction, torque. So we need the scope, not just measure the three-phase control signal. We also need to access to this kind of sensor signals. It need multiple channel of scopes. So normally we have provide 6 channel or 8 channel scopes for this kind of measurement. And another thing is that normally we need to, using DQ0 analysis on the control logic to see how this DQ0 algorithm is good or not. In traditional way, we don't have this kind of calculation, but right now in our software, we can convert this kind of three-phase AC signals into those DQ0, diagram to see this kind of control algorithm is really working or not. Engineers really like this, so we go through a little bit fast. Another good thing is that for this kind of MDA software, you can do the dynamic analysis of the motor. Here you can see it's unlike some power analyzer. It's doing, the statistic analysis. Maybe it's accurate, but normally we also care about for example, the start and the stop status of the motor to see if it's good or not. That's the good thing of the scope. And also this MDA software, you can provide the time chain, the acquisition chain. You can see it takes 100 acquisition of different test items to see how the power or how this kind of measurements will vary during the time or during the working situations. You also can access to the sensors to make the mechanical analysis. Here you can see that with this kind of dynamic time trend, you can also doing this kind of mechanical analysis to see how the motor speed changed. For example, here through the time, and the motor start and stop tensions. So the DQ0 is really a good feature of our MDA in our softwares. So here you can see easily. It's not just like we mentioned before, the three-phase voltage and current, but with the DQ0, you can see this kind of vector graphics to see the curve or to see the circle is good enough or not. It's very interesting. Normally when we visit a BYD, when they first saw the DQ0 of this kind of phase angles, they are really happy. They ask a lot of engineers from other departments come and see. That's the functions they want because they want to know if the control, the algorithm is good enough. And also we provide a Texscope PC analysis too, which has the same user interface and same options as we seen in the scope. So people from every team, from every department can work offline to analyze the waveform. And also you can connect multiple scopes to do even more channel measurement at the same time. You can use LAN to connect up to 32 channels right now. And so right now we have the power analyze software, wideband gap, DBT options, and also the IMDA options to bring all this measurement together to facing the challenge of the EV powertrain measurement. And we also have a lot of third-party corporations to doing all this kind of semiconductor measurement, or either from the device to module to the system. Okay, and you have mentioned maybe all the powertrain solutions above. And then we also have some ADAS, measurement solutions in the automotive Ethernet. So if you are interested, maybe we can talk about later because the time is limited. Sorry about that. But just know that we can have the automotive Ethernet from 10 megahertz up to multi-giga automotive Ethernet test solutions. Okay, I think that's all for today. So sorry for the delay. And do you have any questions?
Yeah. Thank you, Liu Jian, for the presentation. I think there's one question from Saddam Hakim. I think, how can Tektronix equipment be used to test the efficiency and power loss in the EV motor controller?
Sorry, what power loss?
How can Tektronix equipment be used to test the efficiency and power loss in EV motor controller?
Can you speak a little bit slower? I still didn't quite. In the chat
Yeah.
window?
In the chat.
Okay. Yeah, normally, we are using, we're measuring the voltage and current of our systems. The efficiency or the power losses happened on, the turn on and turn off areas. So the software can find out the areas they want. So let me connect to a scope. Maybe it's more easy for us to understand. Okay, so here we can see an easy demo for the power measurements. For example, if the loss has a lot of loss. We have the switching loss, and also we have the magnetic loss, as we mentioned before. So we just look at this example waveform. So we need to know the switching loss, right? And we have the measurement here. We double click here. You can see that it can specify first the voltage and the current source of our signal, and then you can see that we can set up the reference levels for on and off. For example, the T on and T off start stop current level is 5%, right? Here is also the voltage level. It's also 5%. This is what we can, identify. For example, 10%. And here we can see, for example, T off, right? We can see the red annotation here. So in fact, this is the power by it's a voltage multiplied by current. We get the power, the curves. So we have the definition for the turn on and turn off. So the software can automatically calculate this area, to get the power loss. That's the basic, theory about this. And also, when it comes to the power measurement, we have a lot of other examples, like the power efficiency, for example, here. You see, we also measure the voltage and the current here, and you can see we can specify the input and the output. Then you can calculate. We have the input voltage and current. We have output voltage and current. Then we can calculate the input and output power. The losses. Quite straightforward. I don't know if it answer your question or not. So here we can see the efficiency of the power. The input power, the average is 1.4 watt, and the output is 500 milliwatts, and can calculate all these results. And if it comes to the power quality here, since our voltage and the current has some phase difference, it will cause our output, the power efficiency is not good enough. But anyway, the software can measure this. I can add a result table of the measurement. So here you can see the power quality measurements, like the crest factor, like the true power, reactive power, even the phase angle. All this kind of can be measured by algorithm on the voltage and current waveforms. That's how this works. So, did this answer your question?
Yeah, I think it should be enough to answer the question. Yeah. Maybe if there's any other question, can email me at sales@haliatech.com or email Yujian or Bernard. Yeah. I think that's it for today's session. Thank you. Oh, I'm going to raise hand.
Okay, thank you.